if we look at the pH scale, we see that it kind of looks like half of a bow tie, meaning that the ends, so the extremities of the scale, because the pH scale is a man-made invention. Okay, it's a man-made scale to actually measure or classify substances in terms of their acidity or basicity. Okay, how basic they are or how acidic they are. All right, and that has everything to do with what makes a substance acidic. Okay, what makes that substance, why is it that substance becomes acidic, and why is it that substance becomes basic? In order for something to become acidic, we need to have what kind of ion present? We need to have a hydrogen ion. So, we know that when substances are acidic, they have hydrogen in them. Okay, they've got a lot of hydrogen in them. And the further away you go from a pH of 7, which is dead center of your scale, okay, pH of 7 is perfectly neutral. It is neither acidic nor basic. The further away you go in each direction, the more acidic or the more basic something becomes. So something with a pH of 6, let's say, is considered acidic, but it is much less acidic than something with a pH of 2. And why we actually drew the pH scale like this is because for every numerical step that we get further away from 7, think of it this way. The arrow here is the concentration of hydrogen ions in the substance. What is happening to this arrow when we get further and further away from 7? It is getting longer and longer and longer. So the length of the arrow implies that there's more and more hydrogens in it. The higher the concentration of hydrogens or hydrogen ions in substances, the more acidic it is. The same can be said for a basic substance. Okay? If we look at basic substances, the further we get away from 7, the longer that arrow becomes, which means that the greater the concentration of hydroxide ions, the more hydroxides there are in that substance. Okay? So when we talk about the most common mistakes that people make when they're talking about the pH scale is they assume that the higher up the pH, the more acidic it is. It doesn't make sense for something that has a pH of 7 to have less hydrogens than something that has a pH of 4. Okay, but the further away you get from the middle here, the more acidic or the more basic something becomes. Now, when we actually read the pH scale is what we call logarithmic. Okay? And logarithmic is just a fancy word to say that it works on the premise or the idea of powers of 10. All right? For every step that you take on the pH scale, so something that has a pH of 6 versus something that has a pH of 9. Okay? If we look, now first of all, what does pH even mean? The pH scale, and it's always written with a small p and a big H. What that actually means is the number of hydrogen protons in a substance. Okay? That's what it stands for. pH actually stands for hydrogen protons. Okay? So the more hydrogen something has, the more acidic it is. The less hydrogen something has, okay, the more basic it is. Something that has a pH of 14 is going to have way less hydrogens than something that has a pH of 0. Okay? Now, if we look at these two pHs that were written here, all right? A lot of you have a habit of when we're trying to figure things out, the most common mistakes with saying how much more acidic is something with a pH of 6 than something with a pH of 9. A lot of you will just look at that and you'll say like, okay, well, 1 hop, sorry, that's not a hop. 1 hop, 2 hops, 3 hops, right? Oh, it's 3 times more acidic. No, it is not. Because every one of those hops is a power of 10. So that's like saying, okay, the trick here to find out how much more acidic something is than something else, or how much more basic something is than something else, is saying, okay, well, there were 3 hops here, then it's going to be 10 to the number of hops. Okay? So if you can go with 10, always 10 to the power of, that's what logarithmic means. So if we say, when we're comparing pHs of substances, if we can say, no matter what, it's going to be 10 to the power of, and then the exponent here is going to be the number of hops. Okay? So if we can follow that general rule, we'll stop seeing people say, oh, well, it's 3 hops, so 3 times 10, it's 30 times more acidic. Nope. Oh, it's 3 hops, it's 3 times more acidic. Nope. It's a logarithmic scale. It's 10 to the power of 3, which is what? What is 10 to the power of 3? It's 1,000. Okay? 10 times 10 times 10. 10 times 10 is 100. 100 times 10 is 1,000. Okay? And here's the deal. That means something like distill our spring water. Spring water can often have a pH that's slightly acidic. Okay, pH of 6. Spring water is 1,000 times more acidic than something like baking soda, mixing baking soda in with water. Okay? Does that make sense? If I have a cup of coffee, pH for a cup of coffee is 5. Okay, pH of 5 for a cup of coffee. A cup of milk has a pH of about, let's say, 7.5 or 8. Let's say 8. Okay, or actually we can even give it 7. pH of 7 for milk. How many times more acidic is coffee than milk? 10 to the power of 2, because there's 2 hops there. 5 to 6, 6 to 7. Okay? Think of it this way. Last year, we talked about the digestive system. All right? Last year, we talked about the stomach versus the rest of the digestive system. Your stomach has a pH of anywhere between 1 and 2. Highly acidic. Your stomach produces hydrochloric acid. It is one of the most acidic environments on the planet. Yes, there are substances that are more acidic. Yeah, for sure. But the inside of your stomach at any one time is a very acidic place. How your body actually it copes with that, how it doesn't just eat through the tissue in your stomach, is that your stomach actually is quite protected. It secretes a really thick layer of mucus that kind of coats the inside. But then again, as soon as that soupy mixture, that chyme, leaves the stomach and goes into the duodenum, which is the first part of the small intestine, the intestine has a pH of about 7. Okay, if you go from having a pH of 2 in the stomach to a pH of 7 in the intestines and the rest of the digestive system, all right, you need to actually bring that pH up. That's why your body, the pancreas, is so important for digestion, because as soon as that acidic substance hits the small intestine, it's like, what the heck is this? Ow, this hurts. Okay, it sends a message to the pancreas, and the pancreas starts pumping out sodium bicarbonate. Your pancreas pumps out baking soda, basically. Okay, it pumps out a liquid version of baking soda, which is a base, and it basically brings up the pH. It's really cool stuff. Okay, acids and bases. If our stomach was not acidic, we would not be able to break down fats. We would not be able to break down carbohydrates. All right? It would actually be very, very painful to eat the stuff we eat. So the fact that we need that acid, we're just not equipped to deal with that acid everywhere else. So how many times more acidic is the stomach from the small intestine? If one has a pH of 2 and the other has a pH of 7. So we look at this and we start off at 2, 1, 2, 3, 4, 5. 10 to the 5 is 100,000. Okay, 10 to the 5. Think of it this way. If you're unsure what those numbers are, just put a 1 and however many zeros your exponent is. Okay? So 1 with 5 zeros because it's exponent 5. Okay? That is really, really amazing that our body is able to cope with that. Our body in one instance, and they're literally centimeters, millimeters apart from one another. Okay? Your body goes, there's an area in your body that has a pH of 2, and it goes to a place that has a pH that's 100,000 times less acidic. And your body's able to actually cope with that and fix it. And we're going to talk about something called acid-base neutralization next class.